Hello, everybody, and welcome to thermodynamics. This is chapter number 2. We're starting with new knowledge. We just talked about chapter number 1 in the previous videos. We discussed about thermodynamics, units, things like that, and now we're jumping into deeper concepts. This chapter, particularly, it's one of the most important ones because it talks about energy itself. And as you know, thermodynamics just studies the way we deal with energy, and that's why it's very important. So everybody knows that energy is an important part of most aspect of daily life. The quality of life and even its substance depends on the ability of energy. Therefore, it is very important to have a good understanding of the sources of energy, the conversion of energy from one form to another, and basically the ramifications of this conversion. Energy will exist in many different forms, thermal, mechanical, electrical, chemical, nuclear, but we're jumping into each one of them and defining the ones that we need in order to go, into the next chapter and the different cases. So, as I just explained energy can be in different forms, and we usually are going to learn how we study the energy for particular cases. So if you take a look at this guy right here, basically it's a refrigerator operating with its door open in a well-sealed and well-insulated room. So right here it says that if we take the entire room, including the air of the refrigerator, or fan as a system, which is an adiabatic closed system since the room is well sealed and insulated, and the only energy interaction involved is electrical energy crossing the boundaries of the entire room. As a result of the conversion of the electrical energy consumed by the device to heat, the room temperature will rise. So there is a lot of blah 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 involved in what I just read. And like I told you in the previous videos, you need to read concepts twice and even 3 times in order to understand it better. So basically, this is what it's telling us. So if we take a look at this picture, right? So we have a refrigerator that is connected to an outlet, and then it's in a well-sealed, isolated room, which is telling us that it's an adiabatic system, right? There's no interactions between that. In our system, it's this little box right here that enclose pretty much the room. So now if we have the system, we only study the energy interactions as they cross the boundaries of the system, right? The only way the energy is crossing the boundaries is through the outlet. And that's what we're studying. So if we leave the door open, the temperature of the room will rise. As the result of the conservation of electrical energy consumed by the device to heat, and the temperature will rise. So it sounds like it doesn't make sense because people would think that the energy or the cold air it's coming into the room and therefore the temperature should go down. But what about all the mechanism that it has that is not going anywhere? The heat that that mechanics or the machines inside of the refrigerator, such as pumps and compressor, evaporator, things like that. So what happened with the energy that those systems are releasing? So that energy is coming into my room, and therefore the temperature will rise. But I don't want you to understand that right now because, like I said, we're getting into the definitions. So you have to know just by thinking that the temperature will rise, and if you don't think that way, then keep reading because then you're about to figure it out why. Energy can exist, like I said, in different forms, such as thermal, mechanical, kinetic, potential, electrical, and so on and so forth. And the sum of all of this energy will be called total energy of the system. And this definition right here is quite important because that's what we study at the end of the day. We need to know the total energy of a system at stage number 1 and then compare that with stage number 2 so we can do more calculations. Thermodynamics deals only with the change of the total energy, like I said. you study the states. So if you have one state and then after a while it becomes number two, then you want to know how much energy you have at a state number one and how much energy you have at a state number two, so you can know the interactions between one state and the other. And again, this is just setting grounds for what's coming, calculations and things like that will help you dictate how much energy it's involved in what state and why not. So, but before we get into all of that, and I keep just jumping ahead, we need to define, the different forms of energy. So, and then we're going to start with macroscopic forms of energy. Those are what the system possesses as a whole with respect of some outside reference frame, such as kinetic and potential energy. So everybody's probably familiar with these terms because we've been working with those since, I don't know, physics one. Kinetic energy, everybody knows what that is. So macroscopic forms of energy, I'm going to call macroscopic energy. It's kinetic energy and potential energy. Do you remember what kinetic energy and potential energy is? I'm just going to tell you the definition, all right, with the best of my words. So it's the energy that the system possesses as a result of its motion relative to some reference frame. That's what kinetic energy is. And kinetic energy, if you don't remember, it's a formula that should be something like the mass that multiplies velocity to the square divided by 2, if I'm not mistaken, okay? And that's in kilojoules. That's again from physics 1. Then we have potential energy, which is the energy that the system possesses as a result of its elevation in a gravitational field. Okay, and if you don't remember that, I believe the formula is mgh. Okay, m as a mass, g as gravity, and h as a height. Okay, both of them are just related to a reference point or reference frame. Okay, that's why they're called macroscopic forms of energy. Now we're going to talk about the microscopic forms of energy. These ones are just related to the molecular structure of the system, okay, and the degree of the molecular activity. They're independent of an outside reference frames, okay, or reference frame. So the sum of all those microscopic forms of energy, it's called internal energy. And that's how we call it. So microscopic, I'm just going to go like this. Microscopic energy is pretty much what we call internal energy and is denoted with a little u. Okay, so it's right here. Microscopic energy is those related to the molecular structure of a system and the degree of the molecular activity, and then the sum of all these energy are called internal energy, and it's denoted with the letter U. So at least 6 forms of energy are encountered in bringing power from a nuclear plant to your home: nuclear, thermal, mechanical, kinetic, magnetic, and electrical. And again, there's so many more things involved in this, but I'm just, telling you a little bit about those. Kinetic energy, as I told you, is the energy that a system possesses as a result of its motion relative to some reference frame. The potential energy is the energy that a system possesses as a result of its elevation in a gravitational field. Okay, that's again from physics 1. So we know that kinetic energy, it's equals to mass that multiplies velocity to the square over 2, then kinetic energy, or kinetic energy per unit mass, as I call it, is velocity to the square divided by 2. Potential energy, it's equals to mgz, or as I said it, mgh, being mass, gravity, and height. And then the potential energy per unit mass is just, the thing divided by the mass, which is gh. Something very important, guys, and I know that probably by now you've already read that, But in the book, you're going to have a lot of definitions. So when you see Ke, that's equals to potential kinetic energy, and it's denoted in energy units, which is kilojoules. But then when you see the little key E in, this is capital letters and this is like the little letters, then this one would be energy per unit mass. Okay, so Ke is nothing more than little Ke divided by the mass. And that right there will work with kinetic energy, with potential energy, with all of them. Okay, so you better get familiar with this terminology because we're gonna be using that a lot. So if we have potential energy with capital letters, that's potential energy, like I said. And then if you have the little PE, that means potential energy per unit mass. So PE, the little PE, it's equals to PE over mass. Okay? So when we get into the E as a capital letters would be the total energy of the system. And the total energy of the system is internal energy plus kinetic energy plus potential energy. Or if I go a little deeper, would be U as internal energy plus the formula for kinetic energy plus the formula for potential energy. If you want to know energy per unit mass, it's denoted with the little e, which is equals to the little u. Sorry, guys. So if you want to know the calculations for energy of a system per unit mass, is the little e, which is equals to the little u plus the little ke plus the little pe, and this is not more than the little u plus b to the square divided by 2 plus gh. Okay, this slide right here, guys, you have to keep it with yourself because you're going to need that for all the exercises that are about to come. And now we're going to define something very, very, but very important. You have no idea how important this is, okay? It's a new formula that is totally new to you, probably, and you're going to be using the formula moving on, okay? And all the way to heat transfer when you get to heat transfer if you're a mechanical engineer. Mass and energy flow rates associated with the flow of steam in a pipe of inner diameter with an average velocity of V average. That's what is called the mass flow rate. Okay, so basically you have a lot of different streaming of water or any other substances that are going inside of a pipe. They get through a cross-sectional area with a velocity, and they get to be called mass flow rate. The mass flow rate can be used to basically dictate the energy flow rate, the heat flow rate, the work flow rate, and anything that has flow rate. The mass flow rate is very important because it tells you the rate, how the mass changes with the time. If you have the energy flow rate, then that will be how the energy is changing with the time. So you are going to use a mass flow rate to dictate all these calculations moving forward. So mass flow rate is not equals, it's equals to density, cross-sectional area, and average velocity. And I'm gonna develop this equation a little bit more. Okay, the energy flow rate, which is E dot, it's equals to the E, right, which is the energy times, the little e times the mass flow rate. So basically we're going to develop the equation for mass flow rate, as I call it, m dot. And we know that the equation we got in the previous slide was equals to density times cross-sectional area times average velocity. The units for this guy would be kilograms per second. And this is where we're going to. This is our final product. So how do I get to start? Okay, so mass flow rate is also known as density times volume flow rate. Volume flow rate is nothing more than the volume over time. And what is a volume? How do I start giving just like an example? And then for any engineering calculations, we have to take a little differential or a little cube of water. So if you have a little cube of water, what is the phase of, basically you know that the volume will be all the sizes, so large times length times width times height, right? But then I'm gonna do it differently. This guy right here is a cross-sectional area, and this guy I'm gonna call it distance. So the volume of that little cube is the cross-sectional area times distance. So I'm going to plug this equation into the previous one, which is this. So volume flow rate will be equals to cross-sectional area times distance over time. And from physics 1, if we were to be in a classroom, I will ask you this question, but I'm just going to go right into the answer. But what is distance over time? Distance over time is something that we call velocity, or V with the little arrow. Okay? That's velocity. And we have to know that velocity is distance over time. And the units for velocity, it's meters per second. And don't forget that. That's from physics 1, like I said. So if I get to replace that into the equation, my volume flow rate is equal to the cross-sectional area times velocity. But what happened with velocity? When you have a pipe and you have something that is coming into a pipe, doesn't matter the substance, and you have a fluid that has a velocity coming into the pipe or coming out of the pipe, the velocity will behave like this. It'll be different at any point. Okay, so if you go on top, then the velocity will be different than if you are in the middle. So in order to simplify our engineering calculations, we're going to take an average that falls right in the middle. And that point is going to be called a V average. So this volume flow rate can be now rewritten as cross-sectional area times an average velocity. And if I take this guy into the equation right here, I'm going to get that mass flow rate is equals to density times cross-sectional area times average velocity. And again, the unit's very important, kilograms per second. So this equation right here, it's super, super important. Because with that, you can get the energy flow rate. You can also get the heat flow rate. And you can also get, I don't want to get anything farther than this. Okay, so energy flow rate, again, it's equals to the little e times m dot, or mass flow rate. This is all explained in the book, and I'm just trying to give you a little explanation of what it is, so it helps us to make sense a little bit more, okay? So if I go to the next slide, we get into mechanical energy. Basically, the mechanical energy is what we study, because most of the engineering devices will work under the mechanical, they will produce mechanical energy, or they will have mechanical energy involved, and therefore we need to study that form of energy. So mechanical energy is defined as a form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device, such as an ideal turbine. Pumps are also involved. All of them are also involved. So What we have involved in this kind of energy is kinetic and potential energy. So the familiar form of mechanical energy, that's what people usually knows, right? So potential energy, we know if we go with the mechanical energy of a flowing fluid per unit mass, I'm gonna call little e mechanical, it's equals to the potential energy plus kinetic energy plus the energy of a fluid. Okay? And what is the energy of a fluid? When you're working with machines like this one, for example, let's call a turbine or a pump, you have kinetic energy and potential energy, yeah, for sure. But also you have the energy that the fluid is carrying into the machine and out of the machine. So when you study the machine and you see the entrance and the outside of the machine, there are two different measures of energy at that point, and most of that energy is carried by the fluid. And that's what we call the working fluid energy. All right, and this is this one right here. So mechanical energy of a flowing fluid per unit mass, again, I'm just gonna put it right here. It's equals to B to the square divided by 2 plus GH plus the energy of the fluid. And I'm just going to tell you right now how to get that as a formula, and later in chapter number 3 I'm going to deduct that formula. But anyways, this is equals to the pressure over density. Okay, and for this element right now, don't worry that much, okay, because we are going to get into that in chapter number 3. So the rate of mechanical energy of a flowing fluid, how do we calculate that? So every time you see the word rate, the dot will have to be involved, okay, or the mass flow rate, because we're trying to find the rate. How do I calculate that? So the rate of a working fluid, like mechanically, will be equals to basically the mass flow rate times little me, which is this one right there. Okay, and if I plug this into the equation, is basically the mass flow, it is basically the mass flow rate that multiplies P squared over 2 plus GH plus pressure over density, and that's a formula. So what about if now I need to know the mechanical energy change of a fluid during incompressible flow per unit mass? That's a lot of words, okay? But let's just focus on these ones. Mechanical energy change, that's it. Okay, mechanical energy change of a fluid. And forget about the rest, okay? So if you want to know the mechanical energy change of a fluid, how can you define any change? So any change will be defined by delta, right? Delta of the little e mechanically. Okay, and this is nothing more than E2 minus E1. That's all it is. Simple as that. And how do I calculate E2 minus E1? So you have the mechanical energy right here, the formula. So you have to calculate that at the second stage minus the first stage. How do I do that? Okay, I'm just going to rewrite the equation for you. P2 minus P1 divided by density. The density will not change with the state. Then we have B2 to the square minus B1 to the square divided by 2. I'm gonna use parentheses for this one. And then we're gonna have gravity that multiplies H2 minus H1. And this is the formula. Okay, don't worry. We're gonna use that formula a lot, okay, in the coming chapter. And now, rate of mechanical energy change of a fluid during incompressible flow. Again, only focus on rate of mechanical energy change of a fluid. Okay, you can divide all the definitions by little parts so you can understand them better. So the rate of mechanical energy change, two things have to come to your mind. One would be rate, it's always mass flow rate, and change will be always involve delta. So they're just asking us for the change of the energy mechanically, which is nothing more than mass flow rate that multiplies delta of the little e mechanically. So if I use the equation again, it'll be mass flow rate that multiplies P2 minus P1 over density plus B2 to the square minus B1 to the square divided by 2 plus gravity that multiplies H2 minus H1. And that's a formula right there. So we keep studying the forms of energy, and mechanical energy, it's one of the most important ones. We've been talking a lot about them, and the real reason is because most of the engineering devices will work under the functioning of mechanical components. At the end of the day, mechanical energy is a useful concept for flows that do not involve significant heat transfer or energy conversions, such as flow of a gasoline from an underground tank into a car. So basically, like I said, most of the engineering devices will work by using mechanical energy. And they're more important devices such as, turbines, who are going to involve more than just mechanical energy. The total energy of a system can be contained or stored in a system, and thus can be viewed as static forms of energy. The forms of energy not stored in a system can be viewed as dynamic forms of energy or inner energy interactions. The dynamic forms of energy are recognized at the system boundaries as they cross it, and they represent the energy gained or lost by a system during a process. The only two factors of energy interactions associated with the closed systems are heat transfer and work. And finally, we got into something that is very, but very, very important. Okay, but I'm just going to do the same thing as I've been doing from day one. I'm going to read this again. So it says the total energy of a system can be contained or stored in a system, and therefore can be viewed as static forms of energy. The forms of energy not stored in a system can be viewed as dynamic forms of energy. Okay, they're not stored and they just flow, and that's why they're called dynamic forms of energy. They are recognized at the system boundaries as they cross it, and they represent the energy gained or lost by a system during a process. Okay, as it crosses the boundaries, the system will realize the loss or gain of that energy itself. The only two forms of energy interactions associated with the closed systems are heat transfer and work. The difference between heat and work, an energy interaction, is heat transfer if its driving force is a temperature difference, otherwise it's work. So this is very vague per se, but also is the first introduction to heat and work. And as we develop our design intent in thermodynamics, you'll realize that the definitions of heat and work can be more meaningful and you can see it more easily. And now we get to talk about heat. We get to define what heat is. Or I'm not going to say that we get to know exactly what that is, but we need to establish some ground knowledge in order to understand what's coming. And I can assure you guys that once we start throwing some numbers on the exercises, everything makes a little bit more sense. But anyways, heat is a form of energy that is transferred between two systems, system and surroundings, by the virtue of temperature difference. When there is a temperature difference and we look at it, basically there is some sort of heat involved. So heat can be calculated, or it realized that there's some heat interactions as the heat crosses the boundaries. So if you take a look at this picture right here, we have three cans at different temperatures: 5 Celsius, 15 Celsius, and 25 Celsius. So the room air, so this whole thing is open to the room air, which is at 25 Celsius. So what happened with the soda, with the can of soda, when it has 5 Celsius? So something is going to happen. Some heat is going to be transferred into the soda at a rate of 16 joules per second. Okay, so after delta T, that's the amount of energy that will come into the soda. What happened with the other one? This one is at 25 and this is a 15 and the other one is at 25. So some heat is transferring from here to here, because the heat will travel from the high temperature source to the low temperature source. What happened with this third soda? It has 25 Celsius. Since they have the same temperature, there's no heat interactions. Or if you want to see it in another way, you have the soda at first with 5 Celsius, and after a while it goes to 15 Celsius, and after a while it goes to 25 Celsius, and then therefore the heat interaction is closed. If there's no other factors involved, outside factors or things like that. So something very important, and that we need to call it, heat per unit mass is equals to Q over M. But heat as it is, heat is denoted as Q. Okay, that's the symbol for heat. And then if we have heat per unit mass, it'll be the little q, which is equals to Q over mass, and that's kilojoules per kilograms. So amount of heat when heat transfer rate changes with time is nothing more than Q. It's equals to the integral of from T1 to T2 of Q dt, and this is in kilojoules. This formula will be rarely used by us because we don't get that far. This is more for heat transfer and things like that, when we need to know the amount of heat when the heat rate changes with the time. But anyways, it's important that I show it to you, okay? Then we have the amount of heat transfer when heat transfer rate is constant. That's super simple. So basically, Q will be equals to Q dot, which is the heat transfer rate, times delta T, okay? So if we take a look at the potato, and we take the baked potato and we establish the boundaries as the edges of the potato, or the system boundary. So the thermal energy pretty much will go out as the baked potatoes starts to rest, okay? The energy is recognized as the heat transfer only as it crosses the system boundary. So if you have a baked potato and you take it out of the oven and you put it on a surface in your kitchen, you will realize that the temperature of the baked potato will decrease substantially with the time, okay? And this is due to the heat transfer or the heat interactions between the baked potato, fresh out of the oven, and the surroundings of your kitchen. So work. What happened with work? Work, it's pretty much defined as, the energy transfer associated with a force acting through a distance. That's what definition of work. And I'm pretty sure in Physics 1 you had to work with that. So a rising piston, a rotating shaft, an electric wire crossing the system boundaries, all of those things are associated with work interactions. And now we need to have a formal sign convention for both of them. And let me read this little paragraph, but let me give you the heads up that it's going to confuse you pretty much. So heat transfer to a system and work done by a system are positive. Heat transfer from a system and work done on a system are negative. Right now, what I would do, right, let's forget about this for a little bit. Because guys, from experience, I can tell you, from someone who've been teaching this class, I don't know, several times, and as an engineer myself, I can tell you that the definition of this sign convention is a little hard to understand at first. Just put a pin on it and save it, because at the end of the semester, I'm gonna tell you to go back and read that definition so you can understand it in a better way. So I love this alternative way to use a sign convention. So if we are smart enough to detect when the heat and work are coming out of the system or coming into the system, then we don't need time convention. We can basically spend the time realizing how the work is coming out of your system or coming into your system, or how heat is coming out of your system or coming into your system. So by now you know that the heat will travel from the high temperature source to the low temperature source. By knowing that, you can establish either it's coming out or into your system. Okay, so as the sign convention for work and heat, we're going to establish in and out to indicate the direction of each one of them. All right. If you have any questions related with this one, I can show that to you with an example if needed. Heat versus work. Both are recognized at the boundaries of the system as they cross the boundaries. That is, both heat and work are boundary phenomenon, okay, or phenomena. Both are associated with the process and not with the state. Okay, what does it mean? What it means is that you're never gonna see Q1 or Q2, right? Never. You're gonna see Q from 1 to 2. You're never going to see work 1 or work 2. Forget about that. I don't want to see that on the exam. You're going to see work from 1 to 2 or work from 2 to 1. Okay? Just put that in mind. Unlike properties, heat and work has no meaning at a state. So when we are at state number 1 and state number 2, I'm going to teach you how to find temperatures and pressure and things like that related with that particular state. But when we are working with heat and work, there's no way we can calculate that, because we don't have to deal with the state. It has no meaning whatsoever with the state. Okay? You are going to be able to see or calculate how work and heat are acting between two states in a process. Is more related with the path function. So both are path functions, well, like it says, depend on the path followed during a process as well as the end states. Basically 1, 2, 2, 1. That's it. And now we're going to start defining, and we're almost about to end the session, guys, today. So we're going to start defining the different forms of work and how to calculate them. Even though they're going to be provided by a number in the exercise, I need you to know exactly how to calculate them. So there are two requirements for a work interaction between a system and the surroundings. So there must be a force acting on the boundaries, and the boundaries must move. So work is just defined as force times distance. So everybody knows that. So work is defined as force times distance, right? And this is, what is the unit for this guy? It's kilojoules, remember that. Or the definition, when the force is not constant, it's equals to the integral from 1 to 2 force ds, differential of displacement. And this is kilojoules. Basically, you have your distance and the force is moving the box from 1 to 2, and that's how you calculate that. So now we go with electrical work. It's a lot easier. So when potential difference and current remain constant, we can calculate electrical work as voltage times current, delta T. And this is in kilojoules. Or we can calculate the power or electrical power, which is equals to voltage times current. And this is in watts or kilowatts. Okay, next slide. Shaft work. So Shaft work is basically a force F acting through a moment arm R generates a torque, and the force, acts. It will act through a distance S, and that's what is called shaft work. So pretty much we know that the torque it's equals to the driving force, times the radius, and then we also know, or if we solve this for force, force is equals to torque over radius. The displacement, what is the displacement? Pretty much would be equals to 2pr times the revolutions. So if I put that into the equation, so work of the shaft, it's equals to the formula, which is force times displacement. If I put everything on the equation, I know that the force is torque over R, and the displacement it's equals to 2 pi Rn. So if I keep solving this a little bit more, it's 2 pi n t, and this is in kilojoules. All right, so the power transmitted through the shaft is the shaft work done per unit time. And how do we calculate that? So basically, that power of the shaft will be equals to 2 pi the torque that multiplies the number of revolutions per second or per minute. Okay, next slide. Spring work. So everybody's very familiar with the spring work. So when the length of the spring changes by a differential amount of dx under the influence of a force, then the work done it's equals to force dx. Okay, for linear elastic, the displacement S is proportional to the force applied. So pretty much this is a formula. Force is equals to kx, and K is a spring constant work. And if I put everything into the equation, I will have that the work to the spring due to the spring it's equals to 1/2 K and the position of the spring at the end to the square minus the position of the spring at the beginning to the square, and this is in kilojoules. Okay, well, it says right here x1 and x2 is the initial and final displacement of the spring. Okay, at first the rest position and then the final position. Next slide. Okay, so that, guys, will resume for everything as far as from 2.1 to 2.5. Is a lot of content, very, very, very important information about chapter number 2, and definitely is going to help us to understand what's coming in the following, in the rest of the content in the chapter. At this point, it's very and highly important that you go and read the book, and you go and read my notes, and you go and watch my videos. Otherwise, it's going to be very hard for you to understand. I've added some videos to explain a little further what I just explained on this video, but again, this is just informative video. This is pretty much a lecture that I'm sharing with you to help you understand the concepts that you'll find in the book. If you have any questions, you have to contact me using any of the communication channels. All right, thank you very much for listening. Don't forget to like the video or comment or do anything if you need, if you feel it's needed. And thank you very much for your attention.